This is the investigation for descriptive statistics. This is not much of an investigation. It's more of a lecture. And since we are out of school right now, I'm not going to be able to interact with you very much. But I think this will be more efficient than doing this over Zoom. So first we're going to talk about discrete data, and then we're going to talk about continuous data and how we process and display this data. First of all, discrete data, normally what we think of is whole number data is discrete data. Decimal data is normally continuous data. There are some exceptions because basically discrete data just means that you have a limited number of choices for your data. So like even if you have like something that ends in 0.5, let's say you have weights, but your scale only measures 0.0 or 0.5. That, even though it's decimal, is discrete data because you only have a limited number of choices. You have 0, you have 0.5, you have 1, you have 1.5. You see there's a limited number of choices, so discrete data, right? Okay, so let's look at this first example, which is about peas in a pod. So like peas come in these little green pods, and depending on the pod you get a different number of peas in each one. And a farmer did a study of what was the difference between him using fertilizer or not, how many peas does he get in the pod. So the first set of data without fertilizer, you can see that there are many pods he opened up, and some of them had 4 and some of them had 5 and some had 6. Every time he opened one up, he wrote down the number of peas in that pod, and so this is our data here. Okay, so it's just basically a big giant list. Each number is the number of peas in that particular pod. Okay, it's not organized in any way. So the question is, how do you organize this data? What is the best way to organize it? What is the best way to display it? Well, if you look at it right now, why is it hard to figure out anything about this data? Well, you know, the first step you're going to do with this data, let's say that you do an IA or something about some numerical quantity like this. First thing you want to do is you want to put it in order, right? And once you do put it in order, this list would, instead of looking like this big mess, it would be like 3, 3, 3, 3, 3, 3, 4, 4, 4, 4, 4, 4, 5, 5, 5, 5, 5, 5. And you'd have like a bunch of numbers repeated, right? Because like you put them in order, and especially in the case of discrete data, you're going to get repetitions. When you get these repetitions, you might think, well, this is kind of inefficient. I'm going to display a bunch of 3s in a row, a bunch of 4s in a row. First thing someone wants to do is they're going to like count how many 3s there are, count how many 4s there are, right? Instead of just like looking at a bunch of 3s, they're going to maybe arrange it in what we call a frequency table, where in this case we have like, you know, peas in a pod is the quantity to the left side, and the right side is the frequency that we saw each number of peas in the pod. So let's say, how many times did we see 2 peas in a pod? We saw it twice. How many times did we see 3 peas in a pod? We saw it 11 times, okay? So basically what I did here was I went through this list, I counted up how many 2s there were, how many 3s there were, how many 4s there were, all the way to 9. Do you see? So this is called a frequency table. All right, let's move on. Frequency tables are pretty useful, right? They can take that big, long, ugly list and make it into a more compact list, which is easier to process. Next, we're going to have histograms. Histograms, and what you have here in this drawing is not a histogram. This is a bar chart, which you are pretty familiar with from your days of middle school science fair, right? So let me show you some of the differences between a bar chart and science fair. Bar chart and a histogram. So one of the things about histograms is that it's kind of like the x-axis is a number line, and the bars occupy the entire space of the interval that you're talking about. In this particular case, even though our data is either 2, 3, 4, 5, or 6, or 7, it's discrete data, right? Histograms are drawn so that they occupy the entire x-axis, okay? So instead of just having these little bars above each of these numbers, what I'm going to do is I'm going to make a thicker or a wider bar, and this bar is going to touch the next bar. And then the edges of the bar, I'm going to label the edges of the bar. Okay? And so, for example, the edge of this bar here, it's right between 2 and 3. So the edge of this bar must be 2.5. This edge must be 3.5. This edge must be 4.5. Right? I just put a marker right in between the two values, because do you see how it's like exactly in between the two? Okay, 8.5. And last of all, 9.5. Do you see how there is no bar here? Even though there's no bar here, I still put 0.5 here because I'm just continuing on with the same pattern here. So what would be this marker here? Even though there's nothing over here, I'm still going to put a marker which follows this pattern, so I would put 1.5 here, right? And for the x-axis, I would put that this is peas in a pod. And then for the y-axis, I always have frequency. Okay, so whenever you make a histogram, the y-axis is frequency. How do we find extreme data? Well, again, if you don't have your data organized, it's really hard to see extreme data. Extreme data would be a really high number or a really small number compared to the others. Now, in a frequency table, it's pretty easy to see, right? If I had like another line here that was like, I don't know, 14, and there was one P with 14 in it, do you see how that would be an extreme point because it's much higher than 9? Same thing if I had like something like one with 0 in it or something, okay? So that's how you find extreme data with a frequency table. With a histogram, it's even easier. Can you imagine a histogram with extreme data? It would look like this, and then like way out here you might have an isolated bar like that, and this would be the extreme data, right? How do we find the typical pod size? Okay, so first of all, we have a really good first step, which is we had our frequency table. Here's our frequency table. There's 3 ways to classify central tendency, or the typical pod size, and they all start with M. It's mean, median, and mode, okay? Mode is the one that you learn first, in first grade, in fact. In first grade of the AC, they teach you mode. They do that by showing you bar charts, or histograms, that look kind of like this, and a first grader can pick out the mode because what he does is he sees what the tallest bar is. That's the mode, okay? Might be hard to remember what mode means, but remember mode is from the root of the word moda in Portuguese. So it means it's the most popular, right? So the most popular choice here is this tallest bar. And just make sure that you don't say that the frequency of the bar, which is 51, don't say that's the mode, okay? The mode is actually the data point which corresponds to a frequency of 51, which is 6. So the mode in this case is 6. I can identify it because the histogram has the tallest bar. If I look at a frequency table, I can also easily identify the mode because the biggest number in the frequency column corresponds to the mode, okay? And it's a really good thing that mode is so easy to pick out because it's the one central tendency number that does not come up in the calculator. So even if you put this data in the calculator and you asked it to figure out central tendency, the calculator will only figure out mean and median, but not mode, okay? Mean and median. Mean, you kind of know how to do that, right? You could just like take all your numbers here, add them all up, and divide by how many numbers there were, okay? Now, if you have in a frequency table, it's a little bit tricky because, look, there's 2 2s, there's 11 3s, there's 19 4s, so that we don't exactly have it in the normal format where we can just add up a column numbers and divide by how many there are, but we could multiply 2 times 2 because there's 2 2s. We could multiply 3 times 11 because there's 11 3s, and then we get all these intermediate values, and we'll add them all up. It gives us 844, and then we could divide by 150, which is the total number of pea pods that were examined. So 844 divided by 150 gives us 5.63. Okay. Now, of course, a lot of times we'll be doing that with the calculator, and we'll talk about that later. Spread of the pod sizes. Okay, so there's a few different ways, and right now we'll talk about two of them, which are range and standard deviation variance. Okay, so first of all, range is the one that you learned first. Oh, I'm sorry, there's one more. Median. We didn't talk about median, which is another central tendency value. Okay, the median is the middle number. Notice how there's 150 pea pods here. We need the middle one, which would be between the 75th and the 76th pea pod, right? So the way you would find that in a frequency table would be you would start here, and then you would find the 75th one by looking here. These are the first two. No, that wouldn't be the 75th one. This would be 2 plus 11. That would be up to the 13th. Is that 75? No. Then here we would add a 19 to the 13. That would be I don't know, 32 or something. 32, then we add 29, that would be 61. We're still not up to 75. Oh, here we go. Once we get into this group here, we're going to hit the 75th pea pod, and the 75th pea pod obviously has a number of peas of 6. So the median in this case would be 6. Okay? So that was the last central tendency. We did mode, we did median, and we did mean. Now let's talk about central range. So range would just be, you would take the, now remember, when we talk about the spread, what we're talking about is how far apart the different values for pea pods are. The biggest value is 9, the smallest value is 2, and so the easiest measure of spread is to calculate the distance between 9 and 2, the maximum and minimum. And that would be 9 minus 2 equals 7. So basically, the range, or the maximum minus minimum, is 7. That is a measure of spread. Okay? A little bit more sophisticated measure of spread is the standard deviation. Do you see how, like, range doesn't really look at the middle numbers? It only looks at the minimum number, the maximum number. It could have a whole bunch of different things going on in the middle, and spread and range is not going to indicate that. Standard deviation is a little bit like mean, where it takes into account every single pea pod size that exists and gives it an equal weight. So even if only one of the values changes, that's going to change the standard deviation slightly, just like the mean slightly changes when you change one of these numbers. Okay? Standard deviation has a pretty complicated calculation method, which is that it takes each one of these numbers and then it subtracts the mean, and then it takes that difference, it squares it so that there's no negative numbers, and then it averages all those squares. Okay? Another way to calculate it is to take all these numbers, square them, and subtract the square of the mean. Okay? Now, this is a little bit overwhelming right now, I know, but you'll have a little bit more time to digest this later. Okay? But basically here, now you're going to be doing this with a calculator most of the time, but, and when I say do it with the calculator is doing it for you. But if you were going to do this, for example, in an IA or something, you would square each one of these numbers, and then you would multiply the square times the frequency. Okay, so like for example, this square would be 4, this square would be 9. I would multiply 4 times 2, I would multiply 9 times 11, and then by weighting each one of these squares with how many times it occurred, I get this huge number here. I divide by the total number of numbers, and that gives me the sigma value. Okay, we're going to talk about that a little bit more slowly in a future page of the packet. Okay. All right. Now, just to let you know how the calculator calculates these, it does it through data input in stat edit. In stat edit, it basically allows you to input two lists just like this. You can input more often than not, you're going to input two lists. The first list is the data, the second list is the frequency. Okay? What if you get data that looks like page 1? What if you get data that looks like this? You can input this whole list into list 1 and then leave list 2 blank also. Either way, you can use one var stats to calculate many of the values we've been talking about right now. So if you do stat calc one var stats and you say that the list is L1 and the frequency list is blank, like on page 1, or you do the same thing and you say that list is L1 and frequency list is L2, and either way it's going to give you useful information like X bar, which is mean, med, which is median, and of course it doesn't give you mode, remember, and sigma, which is the standard deviation. Okay, oh, one thing I forgot to say about sigma. Sigma is related to something called variance, okay? So when we did this process here, we added up all the squares and we averaged it. That actually gives you variance, okay? Then you take the square root of that, that gives you sigma, okay? So sigma is the square root of variance, because you can see variance is expressed as sigma squared. When you take the square root of it, you just get regular sigma, which is standard deviation, okay? All right. Let's talk a little bit about sampling, okay? So usually when you have a very large population that you need to find out information about, we do something called sampling, where we poll a small part of the population, and then based on our poll, we decide how the larger population is going to behave. Of course, we do that all the time when the government tries to figure out, what the people think, for example, in elections. There's also something called the census. In the census, every 10 years in Brazil and the U.S., people go out and interview citizens to try to figure out what typically citizens possess, how much money they earn, what kind of jobs they do, etc., etc. Okay? And so when you do these kind of samples, including in your IA, there's many different methods you're going to use. The convenience method is just what it sounds like. For example, let's say that I wanted to figure out what is the typical GPA at EAC, okay? And the way I did it was, well, it's very convenient that I have a class of math students in front of me. Why don't I just get all their GPAs, take that average, and I'll assume that that average is the average of the entire upper school. Okay, that's obviously not very correct, but it's one of the easiest methods I could use, right? And that's called convenience method because I am doing something which is quite convenient for me, right? Simple random. So simple random is when let's say I take a list of all the upper school students, I write their names on pieces of paper, and I'm going to draw out 20 pieces of paper randomly, and then based on those 20 pieces of paper, I am going to check those 20 GPAs and take the average of those. Okay, so that would be a simple random sample. Okay, now when I draw those, I'm probably going to get not a proportionate amount of each grade, right? Wouldn't you want like each grade represented in the proportion that they exist, right? So like a grade that has more people, I should take more samples from that grade than a grade that happens to have less people, okay? And that is what we would do when we do stratified or quota, okay? So with stratified, what we do is we divide up the population into like grade 6, grade 7, grade 8, all the way to grade 12, and then we just make sure that we get samples from each one of those groups, okay? Quota, we would be even more careful. We would make sure that, like, instead of just taking an equal number of samples from each grade, let's say that 12th grade has more students than 11th grade does. Let's say that 12th grade has 45 students, 11th grade has 35 students. We would take samples in proportion to the number of students in each grade. Okay? Finally, systemic. Systemic is, let's say that you, instead of taking random draws of pieces of paper with names on it, you could just have a big list of names, and then you would just say, oh, I'm just going to choose every 10th name from the list. That's how I'm going to do my sample. So that's like, even though the result is also a random selection, you are doing it in a systemic way so that you're not having to do random draws. Okay? So this information about how to take samples, this is something new that is in our syllabus starting this year, which it wasn't up till now. Okay? Let's talk about continuous data now. Remember, continuous data is like decimal data. So here is an example from the book of decimal data. Basically, these are distances that a golfer has shot the ball from the tee. Okay, and so these are distances in yards, I think, or meters. And how do we treat this data that is different than the Peapod data? Remember, the Peapod data was all integers. It was numbers basically between 2 and 9. There weren't that many different categories. Look at this, 251.1. Okay, this data is like super specific. I don't think there's any other 251.1s in this whole list. Are we going to group together 251.1s like we did with all the Peapods that had 2 P's in the pod? I don't think we can, because like each one of these, there's only one occurrence, right? So how do we organize this data? What we do is we make groups, and this is called grouped frequency table. So in a group frequency table, what we do is we make intervals, and then each one of these intervals is going to have a bunch of these different numbers in them. And do you see what I'm doing? I'm creating by taking a left number, 240, and then a right number, 245, and I'm putting an X in between with a less than or equal to sign and a less than sign. And do you see how like the left sign is less than or equal to and the right sign is less than? Why am I doing that where one of them is less than or equal to and the other one is less than? Well, the reason why is because let's say that my data point is 245.0. If my data point is 245.0, I need to figure out, by looking at this frequency table, where this falls. Would it fall here, or would it fall here? Well, I can see that 245 would fall in the left one, because in this one, in this one, because do you see how 245 is less than or equal to X? So even if I put 245 into this statement, it would be true, because 245 is less than or equal to 245. Whereas if I tried to put 245 here, 245 is not less than 245, so it doesn't fit here. I want 245 to fall into one of these classes and not into more than one class. So I don't want any overlap, and that's exactly why here I have less than or equal to, and here I have less than. Okay? So that's one thing to be careful of in the frequency table. And so basically the frequency table has these intervals on the left, and then it's got the frequencies on the right. Okay, so it's very similar to the previous frequency table, but it's a little bit different because in this case it has an interval defined by the lower and the upper boundary as opposed to the single number that we had before. Okay? Now here it's very similar the way we create the histogram. Do you see that I mark the edges of each one of these bars? So 240 to 245 is one bar, and 245 to 250 is another bar, and 250 to 255 is another bar. Do you see how by putting these numbers exactly in between bars, I only have to put 240 once, I only have to 245 once, and then it does double duty, because the first interval is 240 to 245. The second interval is 245 to 250, just like in the frequency table. Okay? And then on the frequency y-axis, you see that I have 1, 2, 3, 4. So each one of these lines is also the number of times that amount occurred. And then I just fill in the blocks according to this. So 1, 3, 4 means height 1, height 3, and height 4. Okay. How do we find the typical distance on a golf drive? Well, again, mean, median, mode. The only tricky thing is, let's say that we're going to put this in the calculator. If we were going to put this in the calculator, what do we put into list 1? Because list 1, normally we put the data. Before we put 2 peas in the pod, 3 peas in the pod. This time we have intervals. So what the heck are we going to put into list 1? Well, what we're going to do is we're going to put the average of the left and the right boundaries. So you take like 275, you add it to 280, and you divide it by 2, you get 277.5. That 277.5 is what goes into list 1. For the first interval from 240 to 245, the middle number would be 242.5. So you use those middle numbers and put them into list 1, not the left and the right boundaries. Okay? Those same midpoint values are going to be used when you figure out standard deviation also, by the way. Okay? All right. When you find mean, median, and mode, there's one thing different though. Since we have chosen to represent each one of these intervals with just the middle value of each one of the intervals, those middle values are representative of all the numbers that are in the interval, but they're not exactly the numbers that are in the interval, right? If you go back, remember what numbers are in 245 to 250. Well, there's 245.1, there's 248, and there's 248.5, or 248.8, right? Now, when we represent that interval with 247.5 and we calculate mean, median, and mode, that is obviously not reflecting exactly what's in there. So when we talk about the mean using this method, we don't say the mean. We say the estimate of the mean, okay? It's a pretty precise calculation, so it doesn't mean we're not doing a precise calculation. What it means is we're making an assumption that this whole interval is represented by the middle number of the interval. Same thing when the calculator figures out the median is going to be indicated by the middle number because you put middle numbers in for the L1 list. And when the calculator calculates the median, it's going to give you one number back, and that number is going to happen to be the middle number of one of these classes. And if it says, for example, that the answer is 262.5 for the median in the calculator, you go back and look at this and you go, okay, 262.5 is the representative number of the 260 to 265 class. So this class is where the median lies. Is the class the median? No, but we know that the median is inside this class. So we say the class where the median lies. For mode, if you find out that this is the most popular class, then we do know that this is the mode class, but we don't know exactly what the mode is, right? So in this case, we say the modal class is 260 is less than or equal to x is less than 265. Okay. Last thing, we're going to talk about the cumulative frequency graph. And one very popular application of it is the SAT exam. Okay, so here what I have is SAT data. And of course, I'm going to concentrate on the math data. And what I'm going to do is I'm going to take their percentiles and I'm going to graph the scores versus the percentiles and see what I get. It turns out that what I get is an S-shaped curve, okay? And it looks like this, okay? And in order to make this S-shaped curve, I construct what I call a cumulative frequency table, okay? Remember frequency table? This is a little bit different than this cumulative frequency table is a little bit different than frequency table because the cumulative frequency table has a steadily increasing number in the frequency column, because instead of being frequency, this is cumulative frequency. And the way you make cumulative frequency from from data from normal frequency is you do a running total of all the frequencies. Okay, so if you go back to one of the frequency tables we made, if you have like 1 and you have 2 and you have 1 and you have 3, you would make a running total by saying, okay, the first number is 1, the second number is 1 plus 2, the third number is 3 plus 1, the fourth number is 4 plus 3 is 7. Do you see? So you make a running total of the numbers here, and that's how you get a steadily increasing number, and that's exactly how they did it for SAT, okay? But in this case, for percentiles, we already have a steadily increasing number, which is the percentile, so I just put them here. Then I'm going to use these numbers, and I'm going to graph. Oh, by the way, when you make a cumulative frequency table, you're also going to have intervals like we talked about before, right? So we got things like 760 is less than or equal to x is less than 800, 720 is less than or equal to x is less than 760, right? So each one of these is an interval which occupies the distance from the previous number to this number, okay? But when you graph it, what you do is you always graph the right number, okay? And we'll talk a little bit more about that when we get to it in the packet, okay? But if I graph everything, it basically looks like this S-curve here, okay? Steadily increasing, just like the cumulative frequency. And on the x-axis, I have my SAT scores. That's my data. And on the y-axis, I have the frequency, the cumulative frequency actually. And in this case, the cumulative frequency is actually a percentile. All right? And when you do a cumulative frequency graph, you're going to plot these points like this. And the next thing you're going to do is you're going to draw a curve as best as you can through all these points. From this cumulative frequency graph, you can see a lot of different things. Okay? One of the things you can see is the median value. How would you find the median value? Well, the median value, remember, is the middle value. The middle value in the 100th percentile is the 50th percentile, so I take the 50, I draw a horizontal line until I get to the red curve, and then I draw a vertical line until I get to the x-axis, and it looks like that corresponds to a value of 490, for example. Okay, so the median in this case is, well, maybe it's like 500. It looks like 500. Oh, what do you know? The median score of the SAT is 500. What about the third quartile, which is the 75th percentile? The 75th percentile I can find using the same method. And it looks like the 75th percentile would be about 590. Okay? What about the 25th percentile? The 25th percentile looks like it would be about 400. Okay? The minimum, of course, is 200. The maximum, of course, is 800. Did you know that I can do what we call a box plot based on these numbers? So a box plot is done by drawing vertical lines at each one of these key numbers. It's called a 5-number summary because there's 5 numbers in it. And like this one here is going to be the 25th percentile. It's called first quartile. This one is the median, which is the 50th percentile. And this one is the 75th percentile, which is the third quartile. And this is the minimum, and this is the maximum. So do you see that each one of the vertical lines represents one of the key 5 numbers, and then you use these 2 whiskers here to connect the min and the max to the central box. And the central box is what contains the middle 50% between the 25th and the 75th percentile. That might sound familiar because the middle 50% is what typically defines a college's SAT scores, right? Their typical SAT scores. And there's the one last concept that I want to present today real quick is the IQR. The interquartile range is the distance from the lowest person in the middle 50% to the highest person in the middle 50%. In this particular case, it would be 590 minus 400 equals 190. So the IQR for this distribution is 190. What would be the range? The range would be 800 minus 200, which would be 600. Okay? but the IQR, or the middle 50%, is something which is a better description of what most of the people in the interval are doing, because most of them are clustered around the center. Okay, and I think that's it. I know that was really long. I know that was a lot of information, but we're going to be going through it slower during the